Okay, at it again here. So I was putting a video up for my class, basically trying to get started with how to graph quadratics. And so I was looking at the video and I always look at something and say, well, I wish I had added that, or at least said that. Because these conversations have to continue, and people have to think about things in order to have time to process repetition. Very important. So this was at the end of a graphical exercise, and I'm going to call this video a graphical exercise part 2. So in the playlist, there is one entitled graphical exercise. All right. And I've decided to pick up where that one left off. I think there's some things that we can learn from it that are helpful. So we're going to continue diving into this thing. And I'm telling you this is a quadratic because x to the fourth and x to the sixth through these two locations would have a similar look, but they'd be different, obviously. So this is a quadratic. So bye-bye. All right, and how do we write that? Well, that's in the other videos. And let's look at quadratic behavior. Let's look at some table values over here. So x is 0, 0 squared is 0, and 3 times 0 squared is 0. And what are we doing? We're looking at a four-sided figure, quad meaning four in Latin. And we're really looking at x to x squared, side length to area. Okay, that's important to know, side length to area. And it's really important to know that you cannot make this area smaller than 0. So quadratics have a minimum. We have a minimum over here. However, it's occurring at -4. Well, I guess -4 has got to become 0 squared. And I don't know any other way to do that than to say over here, oh, this is going to be interesting, x plus 4 squared. All right, so here's the hallmark squaring process. 1 squared 1, 2, 4, and we get 9, 16, 0, 1, 4, 9, 16. And if we triple that, we get 0, 3, 12, 27, 48, if we triple it. All right, now how do you get the a term of a quadratic? It's the change from the vertex. So from -7 to 41, we're going up 48 units. And -4 to 0, if we look at x plus 4, which measures that change, when I put 0 in, I move 4 units to the right. So I've gone over this way 4 units. Okay. And if I want to get these numbers are really all about area, right? X squared is all about area. Well, I need to get what? 48 units of change, because if I go over 4 and square it, I should go up 16, but I'm really going up 48 units of area change. Then it looks to me like, oh boy, is this going to be an awkward video, but I've already got stuff on the board here. Looks to me like 48 units of change occurs when the side length of the square increases by 4, getting 48 more units of change. Okay, and where am I at here? I guess that shows it. So if the typical squaring process changes by 1, 4, 9, 16, then changing by 3 means, or multiplying by 3 means that I'm going to go up 3 units. When I change by 2, 12, 27, 48. I think we can show that over here now. So if I'm tripling the squaring, if I go over 1, I should go up 3 units. If I move 2, I'm going 3 times 4, 12 units. 3 units of squaring gets me 9 units of change. Tripled gets me 27. And then this one here gets me 48. And if I want to get numbers like -7 out of the squaring process, then the last time I have to change this is I've got to change that, and I should get 3 units of change, which puts me at -4, 12 units of change, which puts me at 5, right? There's 12 units of change, 27 units of change, -7 gets me to 20, And going up 48 from -7 takes me to 41. And that's what I have graphed over here. 3 units of change gets me -3, comma, -4. 12 from this gets me -2, +5. 3 units of change from here, because that's what x plus 4 measures. So if I put -1 in, I'm getting 3 units of change. When I square that, I get 9. When I triple it, I get 27. Add it to -7 takes me to a height of 20. And then 48 units of change on top of -7 takes me to 41. Okay, so really what I have is 3 times this x minus x plus 4 times x plus 4 minus 7. That's really the geometric calculation. I'm finding the area, I'm tripling it, and I'm making an adjustment. That's what's going on. And it's most important to know that when you square -1, you get 1, but when you square 0, you don't get anything. And when you square 1, you get another 1. And so we get that signature. Look at this. Oh boy. We get that signature parabolic shape of a graph. And so if you see one of those, probably comes from the squaring process. And it's important to also know how things change. And I think it's important that you see this at the Algebra 1, Algebra 2, or pre-calculus level, because chances are you won't do it at the calculus level, even though this is where derivatives come from, the geometric aspect of the square, right? I think it's what Newton saw. I think he did a squeeze. Now, I'm just looking at a one layering process. That's how I understood it. A one layering process. So if this is area, if I draw and continue to sketch little, what do we want to call those? Perimeter sketches, I'm increasing the area, right? And at what rate? Well, it depends upon the size of the square. So I decided to put 0.00001 as my change in dimension. My 2 by 2 gets me 4 units, originally 4 units of area, but 2.000001. I put a lot of zeros in this time because I'm going to change this table as we go along. Okay, so if I'm doing that, then 1 unit of change gets me, I put the wrong number in, forgot to change one of the numbers. 0.00000004, right? I'm squaring 1, 2, 3, 4, 5, 6 decimals should give me 12 decimals. 1, 2, 3, 4, 5, 6 should have been there. And another 6. 1, 2, 3, 4, 5, 6 gets me that. And I'm saying you can ignore that error. It's so small. 12 decimal places with a 1. We can ignore that. And if you divide these, the rate of change of the squaring at 2 getting me 4 is actually 2 times x. The rate of change is 4. The rate of change at 1 gets me 1 unit of area, but it's going up at 2 to 1. At 3, 9 units of area going up at 6 to 1. So if we came over to this board one last time, at this instant, well, maybe I just stop there and just let you ponder the, I was going to show you some more things, but I'm probably losing you at this point. But if you look at y equals 2x and you compute the area when I go, let's just do it. Let's just look at the area under a curve, just to foster some thinking. So this is 2x, so that's a height of 2, that's a height of 1. As I move to 2, or as I move to 1, over 1, I get 1 unit of area. As I go over 2 units, 2 times 2 is 4. I have a new triangle, a 2 by 4. That's 8 units of area. If I go over 3, I have 6 for a height. 3 times 6, 18, cut in half is 9. I hope you're seeing something materializing here that we've been talking about for the last 5 minutes. All right, and that's what integration is. And that's what these things are all about. the dx in this case is, in this drawing is, I'm representing it as 0.00001, but I'm gonna put infinite number of decimal places here. Right, and I think we're seeing that in the calculations. So if this was a 3 by 3, and this was a 3 by 3, then that becomes 3, this becomes 3, and remember, that's an x distance, that's an x distance, and I'm seeing x times this and x times, I'm seeing x dx happen twice. And if I get that, I get the change in y, change in the area, right? That's my new area. And if I factor out the dx and divide it to the other side, I get what's called the derivative. And that's a formula that finds how things are changing for the function x squared. All right, now I want to put those thoughts in your head. And it doesn't bother me that you don't follow it yet, because most people get done with a calculus class and never know what they're doing except mechanically. And so this gives you a chance, your brain a chance to process some things, because the study came from geometry, geometric shapes. And I think if we start there, we got a better chance of understanding what's going on. So I just threw some random stuff into your head and hope it helps. I better get off here quick before you get mad at me.